This is David Baus from Tektronix. Kicking off the webinar today, first on the agenda, we'll look at the PCI Express specifications. What's the current status? What do these specifications mean? And which ones do you need to focus on for physical layer testing? We'll also look at the evolution of the physical layer, looking back at Gen 4, 16 gigatransfers per second, and looking forward to Gen 6 at 64 gigatransfers per second. However, today we'll focus primarily on Gen 5, which is 32 gigatransfers per second NRZ signaling. For the second agenda item, we will focus on receiver testing at 32 gigatransfers per second. We'll look at different tools and the implications of using a simulation tool versus waveform tool, specifically the impact on calibrating your crosstalk term. We'll look at the meaning of different test points within the channel and how to properly choose your channel. And we'll also discuss tiebreakers. How do you know when you've finally achieved that correct stress die calibration to properly test your receiver? We'll also look at back channel equalization. How do you improve the signal quality of that channel that's used to provide the transmitted data back to the error detector on the BERT? And we'll discuss testing receivers with spread spectrum clocking and how to handle that for Gen 5 and the implications. For the third agenda item, we'll be looking at the Anritsu and Tektronix PCI Express solutions and how they can help you solve your validation and compliance testing needs. And finally, we'll conclude today with a demo showing a fully automated solution, specifically looking at the challenging aspect of calibrating the stress die. This table shows the physical layer evolution, starting at PCI Express 4.0, which is 16 gigatransfers per second. 5.0 is 32 gigatransfers per second, both NRZ. And 6.0 is expected to be 64 gigatransfers per second, PAM4 signaling, and almost certainly will be. The add-in card loss is interesting to look at. So this is a budget that's defined in the CHEM specification. So it's how much loss is allowed for the add-in card that supports this form factor. We see 8 dB at Gen 4 and 9.5 dB at Gen 5, still TBD at Gen 6, but this gives some indication of type of material and also what budget remains for the system as well. There is no hard and fast spec limit for max channel. However, this is somewhat indirectly defined if you look at the receiver test channel that you have to use when you're calibrating your stress die. So that was 27 to 30 dB for 4.0, 34 to 37 at 5.0, and expected to be 30 to 33 for 6.0 at the respective Nyquist. So this gives an indication of the type of reach that must be supported by the receivers. Increasing more complexity in the reference equalization, looking at CTLE and DFE. So CTLE, you've gone from 2 poles and 1 0 to 4 poles and 2 zeros and 6 poles and 3 zeros expected for Gen 6. Also showing the DC gain ranges for each of those standards. Reference DFE, increasing number of taps, 2 to 3 to 16. Looking at the minimum I that's required to be supported by the receiver. For eye width, we've gone from 18.75 picoseconds when operating at 16 gigatransfers per second, cutting that in half for Gen 5, and cutting that into a third for Gen 6 at 3.125 picoseconds, as defined for the top eye, since you now have 3 eyes to consider. The eye height was consistent between Gen 4 and Gen 5, and then dropped by more than a half as we look forward to Gen 6. On-die lane margining, required only for timing for Gen 4, timing and voltage for Gen 5. The same is expected for Gen 6. To achieve these channel reaches and operate at these data rates, we've had to have cleaner and cleaner reference clocks. So the high frequency jitter limit is interesting to consider between the data rates. We've gone from 500 to 150 to 100 femtoseconds expected for Gen 6. So that's the max high frequency jitter allowed. The recent trend we've seen with PCI Express standards is moving from one generation to the next in 2 years. So going from Gen 3 to Gen 4 took nearly 6, but Gen 4 to Gen 5 was a 2-year cadence, and it's also anticipated that Gen 5 to Gen 6 will be a 2-year cadence as well. So quite the acceleration on these standards. So first here, let's look at the 6.0 specification snapshot. So the base specification, this is the first spec that you'll see, and it describes the chip level behavior on all levels of the stack. And currently we've workgroup approved Rev 0.7, which is quite mature and approaching workgroup approval for Rev 0.9 within the electrical working group. The 6.0 CHEM specification, let's discuss that next. So CHEM stands for card electromechanical, and it defines a system and add-in card level behavior. So currently Rev 0.3 has already been workgroup approved. And looking finally at the physical layer test specification, this is a spec that goes into more detail, specifically on testing of transmitters, receivers, for link equalization testing, and PLL bandwidth and peaking. So this spec is also already Rev 0.3 workgroup approved. So not only seeing an acceleration for 6.0 of the base spec, but also the complementary specifications as well. Here is a similar snapshot of the 5.0 specifications. So the base spec was released in Q2 of 2019. This is the spec that describes the chip level behavior. The CHEM specification is extremely close at this point to Rev 1.0 approval and completion. And this is the system level specification. The 5.0 test spec. So this has been Rev 0.5 workgroup approved. However, after the recent PCI SIG correlation event for 32 gig testing, we expect some acceleration here, and hopefully we'll get to a Rev 0.7 really quickly. All the 4.0 specifications have been approved and released. Integrators list testing actually started in August of 2019, so certification is already available. Now we'll do more of a technical deep dive into receiver testing at 32 gigatransfers per second. Here is a functional block diagram for calibrating the stressed die at 32 gigatransfers per second. On the left in the blue box, I consider this to be the source, or in this case, the BERT. I'm showing the MP1900A BERT from Anritsu. So within here, we have a PPG, or pulse pattern generator, that allows us to transmit different signals. We have control over TX equalization with pre-shoot and de-emphasis for Gen 5. There's the ability to inject different amounts of stress. So for Gen 5, we care about adding random jitter and sinusoidal jitter, specifically at 100 megahertz. We also have the ability to add a crosstalk term, differential mode interference, and also a common mode interference term as well. This is all integrated into that instrument. You can see no external couplers. Between the source and on the right, which is the real-time scope, we have a physical channel. And this consists of fixtures, usually CHEM or base fixtures that are sold through the PCI SIG. You can also see a replica channel that is used when you're doing base testing. This is a stand-in for the breakout for TX and RX on that platform. Now on the right, we'll look at the real-time scope. So I'm showing the DPS 70K series SX scope from Tektronix. So this is used to capture the step response or waveform signaling, depending on which tool is utilized. And then we have some post-processing, which is done. We're applying the RX package model, behavioral CTLE and DFE, behavioral CDR. And ultimately, we're trying to calibrate the signal to an I criteria of 15 millivolts and 0.3 UI at a BER target of e to the minus 12. We do this with a couple different knobs. Our largest control consists of channel loss, which we saw when we were looking at the different generations. So here we can actually use that loss range to get close to these eye width and eye height targets. And then we have finer tuning capabilities with sinusoidal jitter and differential mode interference. And ultimately, this is the stressed eye signal that the receiver will see and must operate at successfully to pass the receiver testing criteria. I want to look at a couple of the more nuanced aspects of calibrating the stressed eye at 32 gigatransfers per second. First, I want to look at what I call the TP1 to TP3 cable. So one of the first steps of calibration is where you connect directly from the BERT PPG to the real-time scope with typically a 1 meter or maybe a little bit shorter cable. Sometimes we'll see 292 or 2.4. And we're calibrating the amplitude, the TX equalization, the SJ, and the RJ. So at 16 gig, this cable is actually counted as part of the channel in that range of 27 to 30 dB that's allowed for stressed eye calibration. So effectively, the reference plane is kind of shifted to the output of the PPG. And I think more correctly at 32 gig, what we've done is we've made that reference plane officially at the end of the cable, so we don't count that as part of the channel loss. So now the reference plane is more at the real-time scope for this step, and that's where we actually calibrate those different parameters. So it does not get included in that 34 to 37 dB range. So it is a difference. I want to make sure that's clear between Gen 4 and Gen 5 calibration. Next, let's look at the different tools that we use for evaluating the eye diagram at the end of the channel. So for base testing, historically we've used CSIM, and this is a statistical simulation tool. It takes as an input a step response, and in simulation it adds the different amounts of stress and noise and comes up with an eye diagram based on a statistical model. So this was also allowed for Gen 4 chem stress eye calibration as well. It may be for Gen 5, but historically there's been more of a focus within chem on using SIGTest. So SIGTest is the waveform post-processing method. So for this, we actually transmit the true pattern with the stress and noise added from the BERT, and we capture that at the end of the channel using the real-time scope. So I call this the closed loop method because the waveform itself actually has intrinsic to it all of the stressors that the receiver would actually see. So two different tools, two different methods, definitely worth taking note of and kind of understanding the differences there. So next I want to talk about tiebreakers. So you're going to have a solution space, and that would be different amounts of channel loss, sinusoidal jitter, differential mode interference that get you to that stressed eye target, 15 millivolts, 0.1 UI for Gen 5. So you have to make a decision, which one do you go with? And the base spec actually calls this out pretty clearly. So the first criteria is pick the solution with the highest channel loss. So you're going to want to be trying to find something that's closer to 37 than to 34. If you still have multiple solutions there, then you want to pick one of those solutions with eye height closest to the nominal value of 15 millivolts. We'll actually have a window to find around this. So try to get close to that true 15. And then finally, if no solution exists, there is also an allowance to sweep the amplitude from 720 to 800 millivolts. So typically we don't see this as necessary, but it is a knob that's allowed if you cannot find a solution with channel loss, SJ, or differential mode interference. One element of the stress cocktail that's used at 32 gig is differential mode interference. This is a 2.1 gigahertz sine wave, and it's introduced to emulate what you'd see with crosstalk in a real system. There's an aspect of this that's a little bit tricky to understand, so I wanted to spend a little bit of time on it. This specifically applies when the calibration is done with CSIM, or the simulation approach. So there's two different test points to consider. So TP2, shown as the test point right at the real-time scope, that's actually before we've done some of the post-processing steps. The ones of interest here are adding the package loss for either root or non-root, and also applying the CTLE. So after those post-processing steps, we get to TP2P. This is actually the location where CSIM adds in differential mode interference. However, the base spec defines this value to be at TP2 before the package and the CTLE. So the table below actually shows the impact on this and an adjustment that needs to be made to align with the base spec values. So you have to consider the attenuation from the package and then also the impact from the CTLE. And so what you see is a combined conversion factor, and that's going to be different if you're doing root complex or non-root complex. So you're going to need to make that adjustment to have that alignment with the spec. There's also, since it is dependent on the CTLE, that needs to be considered as well. So you have to know what that optimal CTLE will be. Within the combined solution of Anritsu and Tektronix, we have a method for addressing this and reducing the complexity of this particular aspect. Changing gears now from calibration to test, I want to look at the 32 gig back channel equalization. So you can see the connection diagram on the right. You can see the device under test. You can see the BERT. So we're providing that stress signal to the device under test through a channel, and the receiver will have to take that impaired signal, digitize it, and then send those bits back out of its transmitter. And then the goal at that point is to get that transmitted signal back to the error detector as cleanly as possible without introducing bit errors in what we call that back channel. You can see circled in blue here. So receiver calibration calls for a 34 to 37 dB channel at 16 gigahertz. The add-in card budget for Gen 5 is 9.5 dB. So 5.0 systems could potentially have 27.5 dB of loss, including the mated CHEM connector. Fixturing and cabling could add another 4 dB. So we're looking at close to 30 dB back channel for worst case. This is mostly focused on systems. So for add-in cards performing the RX link equalization testing, receiver testing, we don't expect any sort of equalization on this back channel. However, for systems we do. The Anritsu BERT has a highly capable error detector with very good quality equalization. But across the industry, we do expect to need this when testing systems, given that lossy back channel. And we think what should be considered is an active redriver. And we expect this to be called out in some fashion in the test spec, but that hasn't been introduced quite yet. So the redriver is a nonlinear device, and it has different gain stages and something akin to CTLE that will really boost that signal. So some experimentation has been done here. We've actually seen really good results from using redrivers on the back channel. You can anticipate more information coming on this soon from Anritsu and Tektronix on what that aspect will look like in the combined solution. And we believe this is a very solvable problem based on what we've seen so far with experience between the two companies. Let's talk about spread spectrum clocking, or SSC for short. So this is utilized to spread the EMI energy across a wider frequency band to minimize the impact on other electronic devices. So PCI Express has defined this in the table to the top right, some of the parameters here of interest. So the frequency range is 30 to 33. The deviation is different depending on if you have a common clocked architecture or a SRIS. SRIS is when you have separate clocks between the two sides of a link, and they have separate independent SSC turned on. So you can see that the delta between the two in percent UI, and also the SSC slew rate of 1250 ppm per microsecond. So the question here is, how do we handle the SSC when doing receiver testing? So base testing handles it in a unique way. So they have actually a SSC toned that's part of the JTAL mask that has to be tested separately. However, whenever we're in the KIM space, so we're talking systems and add-in cards, or potentially other form factors, M.2, U.2, how do we handle the SSC since we don't do the jitter tolerance testing? For RX LEQ, we do a BER test. So should the SSC be on or should it be turned off? So add-in cards historically have not tested with SSC. And we have control over that because we provide the ref clock to the add-in card, so we can turn that on or off. That is being reconsidered for Gen 5, so TBD exactly where that will go. However, systems, it's a different situation. So here, the systems have their own ref clock, and maybe they have SSC on, maybe they have it off. Maybe they have the ability to control whether it's on or off. Historically, the test spec didn't speak to this much at all. It was fairly silent. So some systems were tested with SSC on, some were tested with it off, and either was considered a passing result. So there is a push to define this a bit more clearly for Gen 5. So expect more clarity there. One argument to be made is that systems in the field typically will have the SSC turned on, and there is some penalty to that. So a lot of people think it makes more sense to test with that SSC enabled for systems, and some people even think for add-in cards as well. The good news here is that the solution from Anritsu and Tektronix does have the ability to test your receivers at 32 gigatransfers per second with SSC both on and off. So regardless of where the spec lands on this particular point, we've got you covered. I'd like to introduce the complete solution for testing receivers at 32 gig from Anritsu and Tektronix, and then I'll pass it over to G2 to discuss more of the details on the MP1900 BERT, and finally we'll conclude with a demo of the fully automated solution for stress die calibration. Here we're looking at the different connection diagrams for calibrating the stress die at 32 gig. So first let's look at the TP1 calibration diagram. So we can see the Anritsu MP1900A BERT, which is the capable BERT of transmitting 32 gig NRZ signaling. You can also see the Tektronix real-time scope. So this is a 70 gig scope, 200 gigasamples per second, that meets all of the criteria for Gen 5. And this is the connection where we're really looking at amplitude, TX equalization, SJ, and RJ. Next we move to the full channel connection. So this is TP2. We've got a diagram for add-in card and system. Same equipment. You can see the Anritsu BERT, the Tektronix scope. Now we have this channel in between, some additional cabling. So this is where we're looking at that eye diagram and trying to tune the signal to be 15 millivolts and 0.3 UI. A lot of complexity here, but this can be managed with the Tektronix receiver application. So this will be a fully automated solution using this software, which will guide you through all of these steps, make suggestions, and really simplify this process and help you get confidence in your final calibration and achieve that efficiently. Here you can see the connection diagrams for testing your add-in card in your system. This is called the receiver link equalization testing. You can see the Anritsu MP1900A BERT and how that integrates into the channel, the fixtures, and where the DUT is located. You can see the Tektronix receiver application that will control this testing and provide you a full report of the results. Let's talk about the full PCI Express Gen 5 solution landscape for a minute. First, for additional debug capabilities, Tektronix has DPOJet, DSP software, which allows additional insight into jitter analysis. Next, there's SDLA, which has more capabilities around embed, de-embed, clock recovery, and equalization, much that's tailored to PCI Express specifically. For transmitter testing, Tektronix has fully automated solutions using our Tech Express software. For base, chem, ref clock, and ref clock has the ability to call the Silicon Labs tool, which is a very capable analysis tool for ref clock testing, and that's fully integrated into the solution. You can also see test fixtures below. So these are pre-compliance fixtures that are available to support our customers until Gen 5 chem fixtures are available from the PCI SIG. And we've talked a lot about our receiver solution. We've got base, we've got chem, calibration, jitter tolerance testing, RX and TX link equalization testing. A fully automated solution with Tektronix automation controlling the Anritsu MP1900A and the Tektronix real-time scope. Extremely future-proof solution for Gen 6. So anyone looking forward to that. Tektronix is also highly involved in the PCI SIG pathfinding for Gen 6, looking at SNDR, stress die calibration at 64 gigatransfers per second with PAM4, and jitter analysis for J6U and JRMS. To bridge the gap until the PCI SIG has Gen 5 test fixtures available, Tektronix has come out with Gen 5 chem pre-compliance fixtures. So these are available today. So these are chem fixtures, and they come in two different flavors. There's a buy one kit that has a CBB, a CLB that supports a buy 1 and a buy 16 on a motherboard, and a variable ISI board. There's also a buy 16 kit, which has all those boards plus a buy 4 and a buy 8 CLB. They come with MMPX adapters and cables and are expected to have very similar performance to those eventually coming from the PCI SIG. They've been used up to date for calibrating the stress die, for RX and TX LEQ testing, TX testing, signal quality and preset, and add-in card PLL bandwidth. So now I'd like to pass it over to G2 from Anritsu for more discussion and detailed on the Anritsu MP1900A BERT.
Hi, David, thank you very much. This is Mr. Goto with Anritsu. I'm going to present receiver LEQ test and jitter tolerance test. There are 3 steps for receiver LEQ test. The first step is calibration. David already explained in the details. You can see very small eye on the kind of a middle of top, and target eye height is 15 millivolt. Eye width is only 0.3 UI, or 30% of 1 UI, or 9.4 picosecond. That is the target stressed eye. Calibration takes maybe 2-3 hours. It's very difficult, but it is automated. Then once calibration is done, hook up the DUT and make link training test. DUT needs to go to the loopback condition under the stressed eye. And once your DUT goes to the loopback, everything is fine. But in general, you may need to make some troubleshooting I'm going to explain how to make the troubleshoot in this stage later slide. Then, once your DUT goes to the loopback, now the final step is the measurement. Your DUT make loopback and make a BER, bar test, and the criteria is 10 to the minus 12, 0 or 1 error for 125 seconds, almost 2 minutes. That is 95 confidence level. Actually, 0 errors is 98% confidence level of 10 to the minus 12. 1 error is still 91% confidence level. Historically, Gen 3 and Gen 4, 1 errors of 10 to the minus 12, but 30 seconds or 60 seconds. So confidence level is not so high, but Gen 5, 125 seconds. So now more strict. Then once your DUT pass this PER test, now you can make a margin test. We call it jitter tolerance test. That is optional, but it's nice to make that jitter tolerance to know how much margin your DUT has. The first and most critical step for the stable and repeatable receiver test. The key is return path. You need to establish the return path and make sure no errors from your DUT TX to error detector of PER tester part. So minimize the loss and ISI of the return path. But the CTS already specify how to make this connection. So there's very small you can do for this. But anyway, use completely phase match cable for the return path. Use the connectors which has wide bandwidth for 32 gig. At 32 gig, only 1 millimeter cable mismatch length, physical length of the data and data bar, physical length mismatch give 5 picosecond phase difference. So you automatically lose a huge, maybe 20% of phase margin when the return path cable has 1 millimeter difference. So make sure you use phase match cable, low loss cable, enough bandwidth for 32 gigs. So I just recommend like a 40 or 50 gigahertz bandwidth for cable connectors. And once make the connection from your DUT TX to error detector, if you have an ability to make the DUT TX generate a certain pattern like a PRBS pattern, modified compliance pattern, any pattern, you just make a connection to error detector and optimize the CTLE of error detector and optimize the TX preset or emphasis to get error-free. That is the bottom line. Once you have error-free on the return path, now you can start testing your receiver side. As David said, for adding card should be fine because of the error detector sensitivity. But when you make a root complex test, a host system test, and when the return path of the DUT has high loss, you may need redrivers. And I need to make some tests, and up to 18 dB physical loss from your DUT TX to the error detector. No redriver is required. But the worst case, the spec is 26.5 dB loss on the return path. So from 18 to 26.5 dB, you need a redriver to make a host compliance test. So the green trace of this portion, that is a return path. So make sure no errors when you make TX to error detector connection. And once you establish the return path, now make a receiver test. Calibration, this is the calibration block diagram extracted from TechMOI. It's a very detailed, nice, easy to understand MOI. But David already explained this calibration process, so I just skip. But anyway, this is a target stressed eye, and using a scope, you can achieve the stressed eye conditions. And once calibration is done, hook up your DUT. Then first step is make the DUT looped back. So link training start, and the DUT make some handshake with BAD pulse pattern generator and optimize the equalization and get into the looped back conditions. As I said, some DUT may have problems, so I'm going to explain how to make the troubleshoot of that looped back condition. Once you successfully make the DUT looped back, now PER testing. You can manipulate all stress from here and make sure you have no errors for 125 seconds. One error is okay, and your DUT can pass. But if you see some errors, you can adjust the stress and make troubleshooting. Another important step is once the DUT get looped back and you see no errors, just make sure insert errors and your DUT get looped back that error also, and error detector detect that inserted error. So this function here, you can have a function to insert errors. Just make a sanity check of the loopback. Some DUT just spontaneously generates the pattern. In that case, you cannot make any test. If your DUT gets no errors, everything is fine, but sometimes you may see some errors, 10 to the minus 7, 8, or 10, 11, almost there, but some errors. So you can change the preset or cursor of the pulse pattern generator. So should be optimized during the training, but maybe you need to adjust the preset or cursor of PPG, and you can manually change this cursor or preset setting and see what the BR is. Or you can manually adjust the common mode noise, differential mode noise, or SJRJ, and see if what's the major contribution of the errors. This matrix also, you can automatically scan every single combination of cursors, 63 full swing, and green portion, no errors, and yellow portion, some errors, red portion, synchronous, and you can find, okay, this center of the green is the best for your DUT. If you have trouble to make the DUT looped back, you can force the DUT be looped back from the BAT. For Gen 3 and Gen 4, you only have two TS. One is through the recovery, and one is through the configuration. So you can make the DUT looped back. You can force the DUT to be looped back. For Gen 5, you can just bypass Gen 3, Gen 4 training, but just go to Gen 5 and make some training. That is good for establish the return path also. Then, when you have any problem to make your DUT looped back, now there is a strong tool to make the troubleshooting. LTSSM, link training state status machine. You can see every single handshake between BAT and your DUT, and using that LTSSM, you can trigger the scope to capture that problematic sequence. So you can select any item from this LTSSM and generate the trigger to capture the waveform on the scope. Then you can make troubleshooting. So you have digital or protocol information of the problem, and you can see analog information on the scope to make the troubleshooting using this LTSSM, link training state machine. And you can see the details of the LTSSM. LTSSM will tell you timestamp and duration time. So each step, how long it takes. For example, when the DUT gets timed out, you can see, oh, okay, this portion times out, so something wrong with this. And you can see each step of the handshake between BAT PPG, pulse pattern generator, and DUT receiver. Let me just talk about some troubleshooting. So try to link, but never get linked. And from the LTSSM, now DUT always looping like 2.5G, and it doesn't get out from the 2.5G polling. In that case, 90% of this case, maybe no signal or no reference clock. So check the cable and polarity and make sure the reference clock is connected to the compliance board. Error detector side has an automatic detection of the polarity data and data bar, but some DUT, when the data and data bar is flipped, it doesn't work. So check the signal connection, and MMPX, make sure the connection is tightly done, sometimes floating. Okay, so now your DUT gets looped back, but still you see some errors. In that case, you can reduce or kill the stress. So you can manually adjust the SJ, RJ, common mode noise, and differential mode noise. So you can just kill all the stress. And also you can change or reduce the ISI channel. For example, the calibration is done using pair of 33, but just, okay, reduce 1 dB ISI, in that case, from 33 to 31 per channel. Even when you kill all the stress and reduce the ISI channel, you still see some errors. Maybe that error comes from the return path. So go back to the initial stage, most critical stage, to establish the return path. Once your DUT passes the criteria of 10 to the minus 12 under the stress condition, now you can measure the margin of your DUT. One of the most major test criteria is the jitter tolerance test. So once your DUT pass, that is 100 megahertz SJ. So that is a starting point. And from that starting point, you can manually increase the jitter until your DUT start showing some errors, and maximum SJ that generate some errors minus the compliance point SJ. That is your margin. But that is really time-consuming test, so that jitter tolerance test can be automated. You can select a detection search or binary search or upward or downward. But for PCIe, the DUT needs to be trained. So first, you make a training under the compliance test. Then increase the jitter gradually. So I recommend using upward linear or upward log. When you use binary search, it started from a very high amplitude of jitter. So in that case, your DUT may get synchronous or PLL unlocked. And you can specify the pass-fail criteria, error count or error rate. For the jitter tolerance test, so this is a marginal test, so I recommend using like a 10 to the minus 9 and maybe 10 errors. For the future, you can also use a criteria of forward error correction and correctable burst errors for the jitter tolerance test. This slide shows the example of the jitter tolerance test. So 4 different SJ, 100 meg, 10 meg, 1 meg, and 30 kilohertz. And to avoid the DUT PLL unlocked, I specify just 100% margin from the mask and make a quick test. So DUT has 100% margin of all 4 different SJ frequencies. Okay, so this is my last slide. So let's move to the demonstration video.
Hello, I'm Shubhankar, product owner for PCI receiver solution, and I will provide a glimpse of our automated Gen 5 solution, which follows the Gen 5 base chem and phi test specifications. When the user launches the PCI RX test application, a solution suite with all the supported specifications and tests is first presented to the user. For now, we will focus on some of the highlights of chem test application. The specification requires the stress tie calibration to be carried out over an optimum channel and other adjusted stress parameters. Some of these parameters are calibrated under TP3 selection, while the others under TP2. Looking into the TP3 calibration module now, in the left-hand side menu, different calibration parameters like the amplitude, preset, etc. are listed that are necessary for closure of TP3 calibration. The software also provides the TP3 connection diagram for reference, describing the necessary connections. Using the automatic selection or using the buttons below, the user can conveniently progress through the various calibration steps. This module also includes a multi-tone SJ calibration option. To support the JTOL test, where sinusoidal jitter amplitude is swept at various frequencies, the solution enables jitter calibration over different user-defined tones and wide range of amplitudes. The software can perform this measurement accurately and efficiently using the oscilloscope tools and running the SIG test in parallel. The user can save the TP3 report once calibration is completed. Now, the remaining parameters required for stress tie are calibrated under TP2 selection. The user must make a choice between either one of the DUT types, AIC or system, along with the TP3 report to include the relevant sweep parameters. To accommodate the difference in distribution of the physical channel loss encountered by the two types of DUTs, the TP2 calibration connection diagram for each of these are different. Both the connection diagrams are available in the application for convenience of the users. The left-hand side menu lists all the necessary components required for the completion of TP2 calibration. A word about the DMI calibration. The DMI sweep impacts both the eye height and eye width variations. During the tests, the DMI waveform along with the bird intrinsic system noise stresses the DUT but not the scope noise encountered during calibration. Therefore, a precise calibration of DMI with classification between the intrinsic system noise and external scope noise is mandatory. Towards this, our solution uses an innovative procedure that minimizes the impact of scope noise during DMI calibration. This procedure is IP protected. Once the correct channel is identified and optimum CTLE and preset are determined, the stress tie calibration is initiated. During this procedure, the appropriate combination of stresses is arrived at to generate a signal that meets the stress tie targets. The stress tie calibration procedure is longest in terms of execution time, usually extending between 2.5 to 3 hours. We have overcome this issue with an innovative solution. Using certain data processing and modeling techniques, an optimum recipe of the stresses is first estimated and then applied to achieve the target eye width and height. Due to very high prediction accuracy, we can close the calibration rapidly within 40 to 45 minutes without any compromise on performance. That is a huge gain in execution time and a customer delight. This process is also IP protected. The final stresses are then saved for the tests with TP3 and TP2 calibration summary and a detailed description of each calibration result. Our receiver solution also provides a fully automated test suite for RX and TX link equalization and jitter tolerance tests with extensive use of the features available in the bird. Complete flexibility is provided to the user to configure and experiment with the test parameters during link training like the loopback mode, presets, etc. and during execution of the tests with varying stress levels, test duration, software equalization and so on. Detailed reports of RX, TX-LEQ and jitter tolerance tests are available to the user for further analysis.